All right, let's do a little more AP review. This is 2006 ABBC free response 2. It is a calculator problem. So, at an intersection in Thomasville, Oregon, cars turn left at a rate of L of t equals 60 square root of t sine squared of the quantity t over 3 cars per hour. So again, it's important to note that this is a rate, right? So this is a rate. This is the rate that they are turning left, okay? Rate they turn left. And this is, so for 0 to 18, this is the graph. This is a terrible version of the graph, but the actual AP free response has the better version of the graph. So this is L of t, right? So this graph is L of t. To the nearest whole number, find the total number of cars turning left at the intersection over the time from 0 to 18. So this is that first fundamental theorem of calculus, right? If you have a rate and you want the quantity, you integrate, right? So essentially for part A, what we want to do is we want to integrate from 0 to 18 of L of t dt. And that's all we have to write because they called it L of t, but what we have to be able to do is type it in our calculator, right? So I'm going to type this in as my y1, right? I'm going to type this in as y1, but I'm going to use x's, right? So this is my y1. What I'm going to do is I'm going to do function integrate, right, which is math 9, y1 with respect to x from 0 to 18, right? And when I do that, I'm going to get a number that has a decimal, but they said specifically round to the nearest whole number, and the nearest whole number is 1658 cars, right? So that's the nearest whole number because they said round to the nearest whole number, right? They don't always say that, but when they do, you need to make sure you do. So you got 1 point for the setup and 1 point for the answer. You did not have to write L of t, the actual function, in your integral. They called it L of t. You can keep calling it, L of t. Part B, traffic engineers will consider turn restrictions when L of t is greater than 150 cars per hour. Find all values of t for which L of t is greater than 150. Compute the average value of L over this time interval and indicate units of measure. Okay, so the thing is, and again, this is a really crappy version of this graph, but here's 150. So what we have to do is we need to find what these two values are, right? So we have to do second calc intersect, or you have to do this thing minus 150 and second calc 0. It doesn't matter to me which of the ones you do, right? But you need to find those values, right? So if you do that, right? So if you do second calc 0, or if you by doing subtract 150 and second calc 0, or if you do second calc intersect at 150, right? So you might want to put y2 as 150 and your y1 is the rate, and then you second calc intersect. When you do that, you're going to get two t values, right? You should store them. So we're going to go ahead and do that right now. So right, in my, obviously make sure that you're in radian mode, but that kind of hopefully at this point goes without saying. So I put my 60 square root of x, because remember I'm going to use x instead of t, and then the only way to do a sine squared is to do the sine of that quantity x over 3, close the sign out, right, and then square the whole quantity, right? And then my y2, I'm going to do a 150. Now what that means is I need to make sure I adjust my window. I need to make sure that my y window goes to, I don't know, let's just say, we can even just do 250. The safest bet here is to pick almost identically the window that you're given, right? Because you have a window, so why not use it? Now, I like to see my axes, so I put my y's as a little bit of negative, and I'm actually going to make my y scale go by 50s the same way the graph does that I'm looking at. So when I graph it, I should see pretty much the graph that was handed to me. The 150 is going to come on through, and I'm going to second calc intersect to find those 2 points, right? So I'm going to do second calc and pick 5, which is intersect. Now, the easiest option is to go up to the line by pressing up and down because the line will be the shortest distance to get there, right? You can see that the line is the less circuitous path. So I hit enter, 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 and I get the first one as x equals 12.42831. Now I'm going to quit out like we've done before, right? And if I hit the X button now, that number is already going to be there, and I'm going to store that as alpha A. You don't have to pick A, that's what I'm going to pick. I go back and I second calc intersect again. Now, yet again, I'll find myself on the curve. I'd rather be in the line, so I'm going to hit up or down to switch. I'm going to go to the line because that's faster. I get to the point of intersection, enter, enter, enter. And I get my intersection. I quit out. That's now stored as X, so I'm going to store that as alpha B. Okay, so I now have my A and my B. Remember, for the AP sake, you should find those values and write them down once, okay? So the 2 points where L of t equals 150 are at t is approximately 12.42830,953, which I'm going to call A, and at t is approximately 16.12165,686, which I'm going to call B. So I called them A and B, right? So those are my two answers. Now I should indicate units, right? So my answer is hours, right? Hours, right? So those are the first two values, right? Those are the times when they should consider it. Is in this. So if I called this A and this guy B, right? They then ask for the average value. So remember, the average value of the rate is going to be the integral from A to B of L of t dt, and then 1 over b minus a in the front, right? So I can make my calculator do the work, but I have to do the setup. Now, they called this L of t, so I can go ahead and use that setup. I labeled A and B clearly and said which numbers they stood for, so that's absolutely fine. And then I just have to type that in. So since I've stored all that stuff, right, what that's going to look like on my end is in parentheses, I'm going to do 1 divided by parentheses b minus a, because I stored them as b and a in my calculator. Math 9, function integrate, right? y1 with respect to x from a to b, and it's going to give me a value, right? And because it's like this is in hours and this was cars, it should be cars per hour, right? So I go ahead and type that in. When I type it into my calculator, I get 199.426 cars per hour, right? And again, this is what the AP needs to see. They don't need to see the part where you show what you type in your calculator. They're never going to give you credit for calculator syntax, right? Cool. Part C. Traffic engineers will install a light if there is any 2-hour time interval during which the product of the total number of cars turning left and the total number of oncoming cars traveling straight through the intersection is greater than 200,000. In every 2-hour time interval, 500 oncoming cars travel straight through the intersection. Does the intersection require a traffic signal? Explain the reasoning that leads to your answer. All right, cool. So what we're looking for essentially, right? So I'm going to erase the 150 because that's not what we're worried about right now. Okay, so here's how we know if there's going to be a traffic light, right? So we need a light, right? We need a light. This is part C. We need a light if, okay, the product that we get for L of t, right? So if the product that we get for L of t times 500 is greater than or equal to, just greater than 200,000. So 500 times the integral, hang on, 2 hours for the product of the time interval, product of the total number of cars. Okay, so the integral over whatever those 2 hours are, so like I'm just going to say, let's say x to x plus 2, right, of L of t dt is greater than 200,000, right? That's why we would need a light. So I'm going to argue, right, because this is the total number of cars in that 2-hour window. So I'm going to argue if I divide by 500 that if I were to integrate from some x to 2 hours later, which would be x plus 2 of L of t dt, I would need it to be bigger when I divide both sides by 500, right? Right, I'm going to get that ends up being a 400, right? So I need this window, this area, to be bigger than 400, right? So essentially, since this window, right, so this window has a width of 2 hours, right? Like these are the hours on the bottom. So 2 hours times whatever the height of this thing is should be bigger than 400. What that's saying is we need a window, right? We need any 2-hour window where the height of the L of t graph is greater than 200. So the easiest thing to do is look and see if there is a 2-hour window where the height is bigger than 200. So what I'm going to do is I'm going to look on my graph and I'm going to see, is there a time when y1 is greater than 200? The easiest way to find that is to find when y1 is equal to 200 and see, is it 2 hours or more, right? If that height is over 200 for that 2 hours, then I should be fine. So if I go to my y equals, I'm going to change that 150 to a 200. And I'm going to do the same graph I just did. And I'm just going to find the two values for which this thing is higher than 200, if it is, right? So sure enough, it does peak out higher than 200. The question we have to ask ourselves is that window where it's above 200, is that more than 2 hours? So I'm going to do second calc intersect. I'm going to jump up to the line because yet again, that's faster, right? I'm going to scroll over and I'm going to find the first one, okay? So it turns out that the first time, and this time I'm not going to have to reuse this. So since I don't have to reuse it, I'm just going to write it down. So L of t is equal to 200 at t equals 13.253 hours. So if whatever other time I find, and that's approximate, if whatever other time I find is more than 2 hours later, then the answer is yes, they need a traffic light. So I'm going to do second calc intersect. I'm going to scroll over to the second one. And I get 15.323 or 324. So I get the second time is 15.324 hours. And that is more than a 2 hour window, right? Because just barely that's more than 2 hours. So based on that quality, yes, we need a traffic light. So because the graph is above 200, right? So this graph is above 200. So we need a traffic light. So yes, you need a traffic light. Now there's another way to do it. The other way the AP suggested was that you could honestly pretty much guess and check and find that if you were to integrate from, let's say, straight up 13 to 15 of this thing, you get a value that is bigger than 400, right? That's bigger than 400. So 500 times that 431.931 is definitely bigger than the 200,000. So yes, you need a traffic light. So either way you do it, you can figure out that you need a traffic light. Inch this over a little so that you can see that logic. So again, the light, you would need a light because on the window from 13.253 to 15.324, there are more than 200 cars per hour, which means that essentially you'd get an area of more than 400. That area of more than 400 times the 500 would in fact be bigger than 200,000.